Okay, so we're on page 68, and I just want to go over these notes with you. So there's some really important stuff on the right-hand side of your page, and so let's go through that. It says, first of all, that a vector right here is a directed line segment that starts at an initial point and ends at a terminal point. So, and they're usually in some sort of plane. So really, the most important thing for you to take away from this is what you used to call, in geometry, this is what you called a ray. And if you want to find the magnitude or length of a vector, you need to know that magnitude and length are synonyms. And this is the formula right here you're going to need to memorize. And really, this formula's it's using Q. Let me write really quick for you. It's saying that you have 2 points, Q1, comma, Q2, and another point called P1, comma, P2. And all it did was did the distance formula between them. So if you were to just do the distance formula between point Q and P, you'd minus the x's, so Q1 minus P1 squared, and then you'd do Q2 minus P2 squared, which is what happened in the formula, and then you'd square root it. It's really important that you know that this symbol right here means the magnitude of a vector v, or whatever vector you're finding, and then again, you need to know this formula. I need to also let you know, in your notes, you'll notice that letters are bolded. And if a letter's bolded, that's the way that math text tells you that it's a vector. So if you see like a bolded letter V, that's how you know it's a vector. Obviously, we don't expect you to write things in bolded print. So another way that you can do this is you're going to draw a V with a little vector symbol above it. Both of those mean vector. So I'm going to go to the other side of our paper, and it says U, and it's bolded, so vector U is really what you want to say. Vector U is a directed line segment from P, which is 0, 0, to Q at 3, 2. So if I were to do this problem, zoom in for a second. If I were going to do this problem, and I'm going to go from 0, 0 right here to 3, 2. And it's really important that you know that we're going in this direction from 0, 0 to 3, 2. We put a dot, which the dot part is called our tail. This thing over here is called our tail. And this arrow piece up here is called our head. So now we've drawn that vector. Okay, and I did that in black. So now in blue, I'm going to do vector V. It says that vector V is a directed line segment from R, which is at 1, 2, 2, 4, 4. 4, 4. So there's my other vector. So we're going to go back to the note side. And it says over here in my notes, I'm right here. It says if two directed line segments have the same magnitude and same direction, they are equivalent. So pretty much if I were to look at vector U and vector V, I can prove that they are equivalent because I can find both of their magnitudes. They're both pointing in the same direction, so their directions are the same. And if we wanted to find their magnitudes, the magnitude of vector U is just going to be, because I have 0, it's going to be 3 minus 0 squared, which is 9, plus 4 minus 0, or sorry, not 4. 2 minus 0 is 2, and the square root is 4. So the magnitude of vector U is the square root of 13. The magnitude of vector V is going to be the square root of 4 minus 1 is 3. 3 squared is 9. 4 minus 2 is 2 squared is 4. And you can see that this is going to be the square root of 13. So vector V and vector U are equivalent vectors. Okay, I'm going to go back down to the bottom. Okay, so component form of a vector. A vector whose initial point is at the origin is said to be in standard position. So you need its initial point to be at the origin. And if I were to write this in other words, it's like saying its tail is at the origin. And then it says if a vector starts at 0, 0 and is terminated at the point st, then its component form is st, which really all we're doing, if I want to do component form, you're going to do terminal minus initial. So terminal minus, so you want to write down, you always want to do terminal minus initial, and then you're going to do that for the x piece and for the y piece. And so when you write a vector in component form, it's telling you how far total in the x direction you need to go and how far in the y direction you need to go. So if we go to the other side of number 2, it says it says find the component form and magnitude of vector v, and it says the initial point is 4, -7, and the terminal point is -1, 5. So again, I'm going to do my terminal minus my initial, so -1 minus 4, comma, 5 minus -7. Please make sure you're doing terminal minus initial. So -1 minus 4 is -5, and 5 minus a -7 is 12. So my component form of vector v is -5, 12, which means I have a net x movement of -5, and I have a net y movement of 12. So I'm going to go left, from whatever point I'm at, I'm going to go left 5 and up 12. Some other important stuff back on the right side. If both the initial point and terminal point are at 0, 0, it's known as the 0 vector because it has no net movement. And then it also says that the absolute value, or magnitude is how we really read that, the magnitude of vector v is 1, then you have a unit vector. And then the last thing is if you have a vector in component form, it's equal if and only if the x's are equal and the y's are equal. We'll go back over to number 2 really quick. Oops. I need to finish this problem because I also have to find the magnitude of vector v. But I need to tell you a little secret. If you have a vector in component form, all you have to do is square the component pieces and then square root. Because if I was going to do the actual magnitude with the magnitude formula, I would do -1 minus 4, and I'm going to get -5, and then I'm going to have to square it. Well, this right here is exactly what we did right here. So again, I say this. If you have a vector in component form, you don't have to do the whole distance formula because you already really know that its net movement or its x movement is -5, and then you square that. And then to that I'm going to add 12, and I'm going to square that. So this is going to be 25 plus 144, which is going to get me 169, and the square root of 169 is 13. So the magnitude of vector v is 13. Okay, so now I've gone to page 69, and we're going to do some vector math. So the first thing we're going to look at doing is called vector addition. And vector addition is pretty simple, except you have to do one little thing. You have to make sure that the vectors are head to tail. So, so I want to look at doing letter C, and I'm going to do letter C in blue. So what I need to do is I really need to draw each vector. So I'm going to draw vector W first, and since I don't know where to start, I'm going to start at 0, 0, and I know that the net movement is 3 in the x direction and 4 in the y direction. So I'm going to start at 0, 0, and I'm going to go over 3 and up 4. So there's my first vector. And if I want to add vector v to this, I'm going to start where I ended at 3, 4. And to this, I'm going to add -2. So I'm going to go backwards 2. And I'm going to go up 5, 1. And let me extend. So I'm going to go over 2 and up 1, 2, 3, 4, 5. Oops, I went over too far. Should be right here. So if you look at this, its net movement, which you can see, is really to get to my point that I have right here. I really only need to go over 1 and up 9. So that's the resulting vector, because if I wanted to draw from here, from my origin 0, 0, up to that endpoint, that vector that I just drew in yellow, that vector would be called 1, 9. And that's what you get when you do vector v plus vector w. And if you don't agree with me, because my drawing is kind of atrocious, you could easily do -2 plus 3, comma, 5 plus 4, and when you do that, you will still get vector of 1, 9. So let's try doing another one. Okay, so this right here on 3a is called a scalar. So really what you're doing to all of vector v is you are multiplying it by 2. So if I have 2 and then I have my vector v, all this is going to result in is having something that is twice as big. Okay, so let's try this last one right here. So this is v, or w minus v. So w is 3, 4 minus -2, 5. And we're actually going to distribute the negative in because we like adding vectors, not subtracting them. So 3, 4 plus 2, -5. And the resulting vector would be 5, -1. Now I'm going to prove that to you. So I'm going to draw vector v again. W. And w is, you start right here, and you go over 3 and up 4. So there's my vector w. And then I'm going to draw negative v, which means I'm going to invert v. So instead of being -2, 5, I'm going to be 2, 5. So from what I have right here, I am going to go up. Nope, sorry, from here. Okay, so from here I would go over 1, 2. And then I'm going to go down 5, 1, 2, 1, 2, 3, 4, 5. And now if we look at this resulting vector right here that I'm drawing, that vector goes over 5, and it goes down 1, which is exactly what we got right here. So that's all the really important stuff that you're going to need from this page. The last thing I want to make sure that you see is these are just some special properties. You don't have to memorize them, but just be aware of them. If you add vector u plus v, it's the same thing as v plus u, because we know that in adding order doesn't matter. Obviously, a vector plus the 0 vector, because that 0 is bolded, so it's the 0 vector, is still the other vector, just in regular math. A number plus 0 is the other number. Number 5 says that pretty much multiplication doesn't matter. C times d times u is c times d times u. Vector v is distributing. number 7 with C, you can distribute it in. Number 9, that thing out front, and maybe we should talk about this. If you look at all these numbers and properties, if it's not bolded, it's called a scalar. And a scalar is just a number. Just a number. A vector is something that has a magnitude and a direction, and a scalar only has a magnitude. It does not have a direction. And property number 2 is just grouping, that you can do U plus V plus W, or you can do V plus W and then add that to U. And then a vector, for property number 4, a vector plus the opposite of that vector is going to result in the 0 vector. Property number 6 says if you are adding two scalars and then multiplying by U, you can multiply vector U in first and multiply on the two scalars and then add the parts together. And property number 10 says that the vector 1, or the one vector, times any other vector is the original vector. Same thing, 0 times any vector is still going to be 0. If you have any questions, post them on Edmodo, and we will talk about vectors more on Monday.